All right, kids, today's lesson is Climate 5, which is all about heat transfer. For this launch question, it may have been a couple of weeks since you learned about this topic, so if you're stuck, feel free to go back to these Climate 3 slides. They should help you answer this question. So right now, please take a minute, read your question, think about your answer, and then come back for the reveal. All right, welcome back. So this question says the graph below shows the average monthly air temperature for two cities, Vancouver and Winnipeg, which are both in Canada, located at similar latitudes throughout the year. So here we have the solid line, which represents the city of Vancouver and how its temperature changes throughout the year. And then this dashed line represents the city of Winnipeg and how its temperatures fluctuate or change throughout the year. So based on this temperature data, the question wants to know which city, Vancouver or Winnipeg, is most likely coastal. Coastal meaning by a large body of water like an ocean or a sea. All right. So what we learned about in Climate 3 is that oceans moderate the temperatures of nearby cities, meaning that those cities that are close to an ocean are going to have a much smaller range of temperature throughout the year. They're not going to fluctuate or change as much. So looking at these two graphs, it looks like Vancouver has a much smaller temperature range than Winnipeg does. Therefore, Vancouver is the right answer here. It must be the coastal city because its temperature changes much less throughout the year than the city of Winnipeg does. And if we look at our map over here of the northwestern United States and western parts of Canada, we can see that Vancouver is much closer to the Pacific Ocean than Winnipeg is. Winnipeg is much further inland, much further away from that body of water that moderates its temperature. All right. So if you were stuck or a little confused about that, make sure you're reviewing those Climate 3 notes before you move on. All right. So today's lesson is going to feel a little bit out of place in regards to what we've been talking about this unit, which is climate. But when it comes to the next lesson, it's going to play a big role in helping you better understand that. So here we go. Today we're going to talk about how heat energy travels or moves from one place to another. And this happens in three different ways. The first one is called conduction. This is the transfer of heat through contact, and that's mainly happening between solids. So here in the skiff, we can see that we have a match. That match is being held up to a spoon, which is made, of course, of metal. And as one end of that spoon heats up, the heat transfers or moves throughout molecules in that spoon, eventually causing that entire spoon to be hot. So things that are good conductors of heat are usually good conductors of electricity as well. So typically solid objects, especially metals like copper or iron, are both good conductors of heat and electricity. All right, so some examples here, heating a pan on a stove or even burning your feet at the beach is an example of conduction. That heat transfers from that hot sand into your actual body through your feet and then eventually upwards. All right, so conduction, all about contact and solids. The next way that heat energy travels should be really familiar to you. We've talked about it a bunch of times this year, and that is convection. So convection is the transfer of heat due to density differences of both gases and liquids, especially things like air and water. We've learned a bunch of times this year how warm things are less dense because they expand, and cold things are more dense because they contract. All right. So when things become less dense, they rise, right? Heat rises, cool things sink, and that creates those convection currents, as we can see here in this tank of water. Warm stuff is rising, it eventually cools down, and it sinks. All right, so that's just a brief review of convection. So a couple places we've already talked about this year is ocean currents, we've talked about really recently, wind, and then also magma in the asthenosphere, that layer of Earth below the surface. All right, so warm stuff rising, cool stuff sinking, all has to do with convection, and that's always going to happen with gases and liquids. So far, conductions with solids, convection gases and liquids. The third type of energy travel is called radiation. I'm sure you've heard of different types of radiation. Some are kind of harmful, some can be really harmful, and some of them not harmful whatsoever. Right? So radiation is the transfer of heat not through gases, liquids, or solids, but by electromagnetic waves. So the special thing about radiation is that it doesn't need any type of material. It doesn't need a gas, solid, or liquid to travel through, which means is that it's the only form of heat transfer that can occur in space. Space is what we call a vacuum. There's no air, there's no water. It's really just a bunch of nothingness. So in order for heat to come from the sun, travel through space into Earth's atmosphere and eventually heat up Earth's surface, we need radiation for that to happen. Okay, so we're going to talk about these waves again in just a second. All right, but just to summarize the first part of our lesson so far, conduction happens through contact, and that's mainly happening with solids. Convection happens because of density differences, and that's mostly gases and liquids. And then finally, radiation happens through waves. They can move all around and in space. So this picture does a really good summary of the three different types of heat energy transfer. All right. If you're still confused or just want to learn a little bit more about these three different types of heat transfer, make sure you watch this video. It does a pretty good job of summarizing everything we just talked about. Right. But now we're going to talk a little bit more about radiation. Once again, this is going to be a key part of understanding what we're going to talk about in our next lesson, which is the greenhouse effect and how it affects Earth's climate. All right. So back to radiation. We talked about how this is energy moving through waves or electromagnetic waves. So we have to talk about this idea or this definition called the wavelength. A wavelength is the distance between two waves. So here we see some examples down of different wavelengths. Here, these two waves are pretty close together. And as we move further and further to the right side of this chart, we can see the distance between the waves is increasing. Our wavelength is getting bigger and bigger and bigger as these waves are getting more and more and more stretched out. Right, so wavelength is the distance from one wave to the next wave. So different types of radiation, some harmful types, some not so harmful types, it all depends on the wavelength of that type of radiation. The shorter the wavelength, the higher the energy. So looking down here at this chart in the bottom, these are some terms we're going to talk about in a second. But gamma rays all the way to the left, they have a really, really short wavelength. The distance between those waves is much lower or much shorter than the distance between radio waves over here. So gamma rays, really, really, really high energy. Radio waves, not so high energy, much, much lower. So as a result, gamma rays are going to be much more dangerous, much more harmful to humans than radio waves are. We pass through radio waves all the time, don't even notice it because they don't harm us. If you get exposed to gamma rays, that can cause things like cancer and definitely cause a lot of harm to your body. Right? X-rays we're all pretty familiar with. We've all had them done to us at either a doctor's office or a dentist's office. And if you ever notice, if you get an X-ray, the person, the technician giving you that X-ray will always leave the room when they do that. That's because X-rays, being on the left side of this chart with their short wavelength, also have a lot of energy. So if you get exposed to a really, really large amount of X-rays, they can cause damage to your body. So that technician who may be giving hundreds of X-rays every single day, they got to make sure they step out of the room because they're not trying to get exposed that much. But for you, a person who may get an X-ray maybe once a year, twice a year, not that big of a deal to get exposed to that much radiation. Right? Ultraviolet rays or UV rays we've talked about before, that comes from the sun, and that can also be pretty harmful to you as well. That's why it's always important to wear sunscreen outside, especially on a nice sunny day in the summertime, because if you get exposed to too much UV or ultraviolet radiation over time, that can cause things like skin cancer and melanoma. All right. Visible light is the light we can see. We're going to talk about this in a second. And infrared radiation is just heat. Right? The way night vision goggles or thermal cameras work is that even though our eyes can't pick up the heat coming off of somebody's body, that technology or those lenses are made so they can pick up that radiation that the human eye cannot see. All right, moving on. So that brings us to a new chart alert. This is on page 14 of the reference tables. We've already used this page a couple of times within this unit, but we're going to introduce a new chart that's at the bottom of page 14. It's called the electromagnetic spectrum. So here we can see some of those types of radiations we just talked about. We have gamma rays all the way to the left, followed by X-rays, ultraviolet. This little sliver here in the middle is called visible light. Then we have infrared, microwaves, and radio waves. So as we go from left to right on this chart, our wavelength is increasing. Here we see an arrow that says decreasing wavelength. That means the waves are getting shorter. And then over here, we have an arrow that says increasing wavelength, which means they're getting longer. So as we go from left to right, our wavelength increases, and therefore energy decreases. Radio waves, stuff that our cell phones work with, our Wi-Fi works with, not going to be harmful to you. We pass through them all the time. Gamma rays, super, super high energy, they're going to be harmful to you if you pass through them because the energy is so high due to that wavelength being so low. Right? So here's a good summary question. Which type of electromagnetic radiation has the shortest wavelength? Take a second, look at your chart, and think about which one must be the shortest based on what is labeled on that chart there. All right, the answer should have been gamma rays. Because gamma rays are all the way to the left, they must have the shortest wavelength. Once again, as you go from left to right, that wavelength gets longer and longer and longer. All right, so the one part we really didn't talk about too much here yet is visible light. And you'll notice within this little section here, we have some colors labeled: violet, blue, green, yellow, orange, and red. Those are the colors of the rainbow, all the stuff that our eyes have evolved to be able to see. That means that all of these other types of radiation, gamma rays, ultraviolet, microwaves, etc., all of those types of radiation are invisible to the human eye. The only type of energy we've evolved to see are these colors of the rainbow, and when we blend them together, all the other colors that are in between. Right? So that's the way a prism works. When light passes through a prism, it gets scattered into these different wavelengths, and those different wavelengths equal to different colors that our eyes pick up on. Right? So violet has the shortest wavelength, the highest amount of energy. As we go from blue to green to yellow and eventually to red, the wavelength is getting longer and longer and longer and representing lower and lower amounts of energy. So violet has the shortest wavelength, red has the longest wavelength. And once again, we can see that just in the way they're ordered on the scale over here. As we go from left to right, the wavelength is getting longer and longer and longer. If you want to learn a little bit more about the colors we see and the stuff we cannot see, definitely watch this video. It does a really good summary about the electromagnetic spectrum and just what light is in general. All right, moving on. So what does this have to do with climate? The sun, of course, is super, super hot. It's over 10,000 degrees Fahrenheit on the surface, and it gives off tons of radiation. And some of that radiation reaches Earth. That's why we have temperatures that are warm enough for us to live on. It's why we can see sunlight on Earth, etc., etc. So radiation coming from the sun, we give a special name to it, and it's called insolation. And that's a word we call a portmanteau. We took a bunch of different words and kind of smushed them together to make a new word. So insolation, it really stands for incoming solar radiation. In other words, energy coming from the sun and reaching Earth. So the types of radiation we mainly get from the sun are, once again, those UV or ultraviolet rays, visible light, the colors we can see, and then general heat in the form of infrared radiation. You're going to talk about these three types of radiation a little more in our next lesson when we talk about the greenhouse effect. Right? So the reason why this plays in with climate is because the color and texture of a surface is going to affect how much energy or how much insulation it's going to absorb from the sun. Remember, to absorb means to kind of take in. Right? So in general here, surfaces or materials that are darker in color and rougher in texture are going to be better absorbers. They're going to take in way more heat than something that isn't as dark or as rough. So surfaces that are darker and rougher in color are generally going to be warmer than things that are not so dark and rough. So this plays a factor in climate because places like cities, where we take all this regular land and we pave over it with these dark surfaces like blacktop and asphalt, it makes cities a little bit warmer than the surrounding areas because they have surfaces or materials that are way better absorbers. The opposite of dark and rough is, of course, light and smooth. So surfaces or objects that are lighter and smoother are going to be better reflectors. They're going to reflect that heat energy from the sun instead of taking it in. And since they're reflecting more energy than they're taking in, it's going to make them cooler than other surfaces that are darker and rougher. So here, this is a pretty cool image. This is a salt flat from South America, basically a huge flat area made entirely of salt. And the light and smoothness of that salt makes it a really good reflector. You can see the kind of the pattern in the sky here reflected in the salt that this person's walking on. So what are some other reflectors on Earth? What are some other things that help the Earth be a little bit cooler than it should be? right? So it's basically things that are light and smooth. Clouds floating in the atmosphere are great, great reflectors. That's why typically in a really cloudy day where you have a little more shadow being cast upon the earth, it's a little bit cooler than when there's less clouds and when the sun's able to kind of penetrate and get to your skin. So here you can see some clouds floating over Lake near upstate New York, and you can see the shadows beneath them, definitely reflecting that sunlight, blocking it from getting to Earth's surface. Right? Additionally, particles that are floating in the atmosphere can reflect some sunlight. Stuff like dust or smoke, or especially ash from volcanoes, they can rise up in the atmosphere and they can also reflect and block sunlight, making the earth cool down a little bit more. You're going to talk about next week how volcanoes can actually lead to some minor climate change. All right, and then finally, snow and ice on the surface. Snow and ice, both really smooth, really, really light colored, so they also reflect tons of insolation and tons of sunlight. There's actually a thing called snow blindness that can happen to people. Skiers and snowboarders on a really, really sunny day, that snow can reflect so much sunlight that people can actually temporarily go blind because of it. That's why a lot of times you see skiers and snowboarders wearing these really intense goggles or glasses with these really reflective lenses on the surface so it doesn't harm their skin as much. People can actually get really bad sunburns skiing or snowboarding even in the winter time because of how reflective the snow and ice is. All right, so that wraps up our lessons today. That's Climate 5. You have 5 short questions as usual to do after this. You can get to them by clicking this link up here. Make sure you're using your reference tables for that. There's a link to them over here. You just got to use page 14 to answer these few questions. There's actually a lot of interesting stuff to talk about in regards to light and color and the electromagnetic spectrum and radiation in general. So I put some links here if you want to just learn a little bit more. This one is about how humans see light and color. Down here, we have a link with a video that shows you what it would look like to see an ultraviolet light, as many species of birds do. And then here's another link to an article that talks about how some animals and even some people can see way more colors than the average human being can. All right, so thank you for listening, and make sure you're just doing these forms and keeping up with us. We will talk to you soon. Have a good one.